So today we're gonna solve this problem, which looks quite easy. So let's see what it states. So we want to find positive integers such that a divided by b plus b divided by c plus c divided by a is 73. So I already wrote that down, that equation. So let's try how we can rewrite this equation. So basically we get that a squared and then c divided by a, b, c plus let's see, b squared a divided by a, b, c plus, and now we have to multiply with b and c, so we get c squared b divided by abc is equal to 73. Okay, and now let's multiply with the denominator. So what we get is a squared c plus b squared a plus c squared b minus 73 abc is equal to 0. So this already gives us a hint that it could be useful to consider some kind of algebraic geometric or Diophantine methods. So that's also what we're gonna use. One could of course try different means like brute force or yeah, for instance one could look at integral part of these numbers and see if we write a divided by b, no, that's not looking good. So we can write it as this plus something between 0 and 1, so for r in 0, 1. But well, I don't know if it's that promising. At least I couldn't find anything with that method. And well, I'll show you soon how I could solve it. But another method which could be successful would be so we have an equation in 3 variables, and maybe some kind of coppersmith method could be useful, but I don't know that much about it. So, but if any of you could solve it with this method, I would be interested in the solution. So let me show you now how I went about it. So the first thing to note is that this equation is homogeneous in the variables a, b, c. So actually the solutions live in projective space apart from the all zero solution, but we don't care about that because we want positive integers. And now that we have an equation in projective space of degree 3, we could maybe check if we actually have an elliptic curve. And we'll find out that we have an elliptic curve. So let's go to Sage and let's see. So let's first define the polynomial ring in 3 variables over the rational numbers. So let's see, that worked. Okay, so next we'll define our polynomial. So that's gonna be just what we had before. So now with x for a and y for c, y for b, and so on. So x squared times c plus y squared times x plus c squared times y minus then 73 x, y, c. So show you again, that was the equation, and so now we have, so the solutions are the zeros of this polynomial. Okay, so that's our polynomial. Let's see. Okay, that works. That's good. And now the next thing we want to do is we want to get this polynomial in. So we want to see if we have an elliptic curve. So there's a command, that's sage command, which is elliptic curve from cubic, and actually there the top key is quite useful because you can see here the possibilities and you can choose. So we take from cubic and we need to specify which cubic, so that's our polynomial. Then we have to specify a point. Well, let's say, well, actually we don't get a curve, so let me write this. Actually we get a morphism, but I'll come to that in a minute. So we have to specify a point. Let's say we take 1, 0, 0. That should work. That should be a point of the curve. And we set morphism to be true. Okay, let's see what we get here. So we get f. Let's exactly. So now we have the scheme morphism. Well, actually I wanted another elliptic curve. Let's maybe take another point. What about this point? Nope. Well, it shouldn't be that important, but actually I wanted another elliptic curve. Well, let's maybe take another point. I wanted that elliptic curve. Okay, so let's work with that. But I think it should also be okay with the other, so you just have to, well, you have to try, but it should work. Okay, so now we have this elliptic curve and we want to use this elliptic curve. So now that we have a morphism from this, well, actually it's also a curve, but from this curve to the curve here in Weierstrass form, we define our elliptic curve here. So we specify the cubic and we get our elliptic curve. Okay, so that's our elliptic curve, and now we want to get points on this elliptic curve. One thing we could try is we look for, well, let's first see if we know about what we know about the curve. So just to give you a little bit more info about the curve. So no, we don't want the torsion order, we want torsion points. Okay, so we see that the torsion is a cyclic group of order 3. Okay, and next let's look at the analytic. Nope, there should be. Shouldn't there be? Maybe there's no such command. Okay, is there something like rank? Rank, okay, does that work? That works, so our curve has rank 1. Okay, so that's good to know. And now that we know that the curve has rank 1, so as a reminder, you might want to look up the Mordell-Weil theorem, and that says that an elliptic curve is a finitely generated abelian group, so over the rational points of an elliptic curve. Okay, so let's see. So here we get actually points on the curve. That's good. We can use these well, one point. We can use this point, or we can also we have another way of searching for points. So we could, for instance, look at the ELF functions and modular form database, and then let's go here. Okay, it's a little bit slow. So here we have elliptic curves, and now let me see over Q, and yeah, and here we can specify the coefficients. So that's our elliptic curve. Did we find something? Okay, we need the coefficients, right, and not the... Okay, so coefficients should be A1, which would be xy, which would be minus 365. A2 would be A0. A3 should... What do we have? We have a y. Right. Okay, so a y should be minus 125. And so we have A4. Do we have an x? No, actually. So A4 and A6, so that should hopefully be the curve. Let's see if that's it. Okay, and now we get a different looking, well, here it says minimal Weierstrass equation. So let's see if that's the same curve. So let's look for minimal model, run, and we get this curve here. And that's exactly that equation. So we have the same curve. And actually, we also get a point on the curve. So we could now, for instance, say, take the minimal model, which is E dot minimal model. Okay, so that's curve, and now we define a point. So the x coordinate is what I have here. Then we can take the y coordinate to be that. So that's our y coordinate. And now we define a point on this curve. So namely, so on this curve given by this equation now. Oops. Nope, I didn't want to copy anything. So that's that, and then that's our point. And it's also a generator of this rank 1 subgroup. Okay, so that's our point. It should be on the curve, and it is. Otherwise, we would have an error message here. Okay, so that's our point, and now we can go back to the curve, to this curve, and we do this by defining an isomorphism. So we want isomorphism from the minimal model, and then we have here, you also see there are methods for isogenies and stuff like that, and then we have an isomorphism to E. That's the isomorphism, and now let's see what the isomorphism actually is. So this is isomorphism from this elliptic curve to the one given by this equation. And here we get some little more info about the transformation, so you might want to look up what it means, but we don't need it here. So that's fine. So now we could take this point, or we can take the image on the isomorphism. So let's take, so this gives us now a point on the curve, and actually that's a different point than this one, but probably it should be related by torsion. So I think that's, well, actually we can try if, well, I don't know if it's that interesting, so maybe I don't try it, but I guess that this point here is related by one of these torsion points with this point here. Okay, so I mean it's this plus one of these torsion points should be this point. Okay, then okay, what to do next? Now we have a point. Okay, and now what we want to do is we want to go from this point here back to our initial equation, and we do this by Isomorphism f. So, but f goes in the wrong direction. F goes from this equation to this equation, so we need the inverse, and that's f, and let's see, there should be an inverse method, and there is. So that's that, and now let's see, maybe just for illustration, let's make it a little bit more explicit. So let's see that, oops, no, we don't want P, we want Q. Okay, so that's the point, and well, this actually already looks good. I thought we had to do a little more. I thought we would have to add points. Okay, so let's see. So let's take A, B, C to be the coordinates of this point Q, and now we take A to be, or let's maybe, yeah, A to be A times the denominator of A times the denominator of B, so that we get integers. So that's what we want to have, and the same for B and C. Okay, so then we should get integers, and well, they should be positive because the numbers here are positive. And now let's look at A, B, C. Oh yeah, A. No, shouldn't be this. Okay, that's run. That looks wrong. What happened here? Oh, yeah, sure. That was a bad mistake, so that's corrected. That was a programming mistake, so I changed A, and then I used the denominator of the not existing denominator of A, so that's bad, but we can easily fix this. Okay, so that should hopefully work now. Oops, one could, and it still doesn't work. Okay, I have to update this and now it should work. Okay, so that works. And now let's look at the equation once more. So we have a squared c plus b squared a plus c squared b minus 73 abc. So a squared times c plus b squared times a plus c squared times b minus a times b times c, and we get 0, and we have found a solution. So all these numbers are positive, so we have found it. We can actually, if you wanna find smaller solutions, we could look if they have some doesn't this show? Okay, let's run again. We could look for common factors in here, like for instance this here is a 9, which is in all, and then we have a 37, and we could divide by these numbers and then we would get a smaller solution, but it would still be quite big. Okay, so that's how we get a solution. But well, actually that was easier than I expected. So let's maybe see if we can complicate it a little more so that you see a little bit more of the techniques. So let's now say Q is equal to this point instead of the point we have from the L functions and modular forms database. And then now we have another point, and now we have that's what I want. So here we have negative numbers, so we don't yet have what we want, but well, let's say our point is Q, and so actually we would do a loop, but maybe to illustrate, now we would say point, so we add Q again. Well, no, sorry, that was wrong. So we are not actually interested in the point Q, we are interested in the image of this point, and well, that's actually also, yeah, okay, that's gives us also some positive numbers, so I can't complicate it here. Some other means, well, we could try to look at Q plus torsion points. Let's look at the torsion points again. So let's say Q, we want to add the point 0, 125. Okay, now let's see what our Q is now. Okay, let's see, well, that actually seems, as I said before, that actually seems to be this point we got from the L functions and modular forms database, if I see it correctly. So we could check. Note that I've really defined Q, but yeah, that's true. It's the same point. Okay, we have one more possibility. We can, so Q, so we could take, we have this, and then probably we would add again this point. Now what point do we get here? This should be, this is a new one. Okay, now let's say, what is the image? Okay, well, we're running out of luck now. I don't have we didn't find a point where it so far. Well, one could try to look further and look at multiples of this point Q and see if we find something where actually these two coordinates are not positive, but so where one is positive and the other one is negative, or well, both negative, but and then one would try to add points. So one would look at, one would say, for instance, the point is Q plus Q, and then we would look at what we get from here. So we would get, okay, here, yeah, so if we would have chosen this point at first, that would have been a bad choice, because here we have something negative and we're looking for positive solutions. And then yeah, we would try to add multiples of Q. So of course one would make this in a loop if we hadn't actually already solved it. And so now we could look again at f inverse of this point, and this time we would be lucky. So to give a short summary, we transformed this at first, this equation, into this cubic equation in 3 variables. Then we were lucky that this is actually an elliptic curve, so we have this morphism of elliptic curves, and then we find a point on this elliptic curve. So either by looking at this database or by using the generators method, and then now that we have a point, we, if necessary, in our case it wasn't even necessary, we add we take multiples of this point, look every time, transform it back from the elliptic curve to our initial cubic equation, so with this morphism f inverse, and look if we get a positive solution. And of course, if necessary, that's what I did here, we scale, well, not if necessary, it's certainly necessary, or not certainly, but it's mostly necessary, we scale by the denominator so that we get integer solutions, not just rational solutions. Okay, so that was a rather long video, but I hope it gave you some ideas how to solve this problem. And if you have any questions, feel free to ask them. Actually, I'll put some links in the description so that you can see also where some more sources on how to solve easy looking problems like this by means of points on elliptic curves. Okay, so I guess that's it for today. I hope you could understand it, and I hope it was actually fun to learn a little bit about how to solve it and about elliptic curves, and hope to see you next time. Bye.